Alright, in our pursuit of ever more sophisticated approaches to ever more complex problems, we've got here a beam that has a fixed end on the left and a roller on the right. There's a whole lot of things that have been asked here, but the first thing that we're just going to address is coming up with how to estimate what the reactions are. And we're going to use really the principle of superposition, but in a somewhat clever way that ultimately is called the relaxation technique. So one of the things that let's do here is really something we need to do every single time, and that is to consider what the statical classification is of our structure. Right, and that's where we're going to come along and we're going to consider how many reaction components we've got. Right over here at the fixed end, of course, we have a vertical, we have a horizontal, and we have a bending moment. And over here at C, we have then the vertical at that roller. Right, so our total number of reaction components would be 3 plus 1 or 4. We're going to compare that to the number of independent equations of equilibrium that we have. Now we have no special conditions such as hinges, so in 2D then we just have your typical 3, sum of forces of the x, sum of forces of the y, sum of moments about a single point, and given that 4 is greater than 3, what we conclude then is that this is a statically indeterminate structure to the first degree because we're one greater reactant components than we are equations of equilibrium. What this also tells us is that we have one redundant reaction, one more than we need for just pure static equilibrium requirements alone. Right? And in the relaxation technique, that tells us something pretty important about how we're going to approach this. So what we're going to do is we're going to relax our redundant reaction. Now when we do this, we have to leave ourselves with a stable structure, and that means we could not get rid of AX. Even though AX is 0 here, we couldn't get rid of it because then this thing could slide back and forth if there were to be an applied force in the horizontal direction. So that's not one of our choices. But the other 3 could be a possible selection. What we're going to do is we're going to select CY to remove. Right? And when we do that, what we're going to be left with is a statically determinate structure, and on that statically determinate structure we'll have the original loads, this distributed load and the concentrated force, and under that set of loads then of course the structure is going to deflect and it's going to violate the original conditions of the structure. Right, that we're going to have out here at C, where we removed this redundant reaction, where we've allowed that value of the reaction to be 0 by getting rid of it. We're going to have a negative displacement. Right? Back up here in the original model, there's our positive direction for delta C, and of course that actually equals 0 in the original structure. Right? And what we're going to do is we're going to figure out how much delta C goes down, and then we're going to push that back into place such that we do end up with delta C equal to 0. Now, this particular case that we've got of a cantilever being with a distributed load and a concentrated load not at the end is going to not be found in any easy table, but we are going to use superposition here because it's nice and convenient to do so. We can put just the distributed load on the cantilever and allow the structure to deform, and then we can add to that what happens with just the concentrated load, not at the end but at that 6-foot mark. And let's see, that's going to be 10 kips here and 5 kips per foot for the distributed load. And so when we go and take a look at what's going on, in both cases here the deflected shape will look similar. Right? The displacement out here is going to be minus 5WL to the fourth, no it's not, over 8EI. Well, that part's right, the 5 is not. I started thinking about a simply supported beam and a distributed load. Now where did I find that? Well, I went into a handy then table of common situations, and here's our distributed load that's uniform with a cantilever beam, and the max displacement happens to be out the end, which is where we are looking for things. There's your WL to the fourth over 80I. Right? That's where that came from, as opposed to just deriving it, which we could also do. And then we've got then our situation over here. Now I've only drawn that part way because I want to emphasize something pretty important, and that is that this load is not out at the tip. If we were to look at the moment diagram, we've done this a number of times for this kind of situation, we would know that the moment of this force increases linearly as we walk our way from the point of load application over to the cantilever end, or rather, sorry, the fixed end, and that will just increase linearly. That distance is 6 feet, so if we cared, it'd be a minus 60 kip foot for the moment diagram. Over here at the far left, it would be triangular. This piece out here at the right doesn't have any moment. It means it doesn't have any curvature. And so that means that we actually have a straight line segment here where we have to know what the rotation or the slope is right here at the 6 foot point, and then we have to extend that on out. So that means that this total displacement that we want out here at the edge is comprised of two pieces. This piece here at B, and then this little piece that really is a little triangle that shows up right there. Right, and that little piece is going to turn out to be 2 foot times theta b. And you're like, where did that come from? Well, here's where it comes from. One, this horizontal leftover length is 2 feet. Right, that comes from up here in the problem statement. And then if this is a triangle, then let's expand this slightly, make this a little bit bigger, easier to see. Here's your 2 foot, and that is theta b. That happens to slope at B. That location right there is point B. Right? And opposite over adjacent equals tangent of theta. But since tangent of theta is approximately equal to theta, then that's where I can say if I want this value right here, I just take opposite over adjacent is equal to tangent theta equals theta, so therefore this is equal to 2 foot times theta b is where that comes from. You have to keep track of the units there. This is grossly exaggerated. This is nowhere near the actual real scale of what's going on here at all. Right? It is very, very small angle in radians that we've got here. Right? So this delta CO is going to be a combination of what we have here in the first one, minus WL to the fourth over 8EI. And then we've got a plus, what turns out to be a minus, really. It goes downwards, right? So that's going to be then, well, effectively what happens, the displacement under the point load on a cantilever, PL cubed over 3EI. But the L is not the total length 8 feet, it's this distance out. It's that little portion right here. So that would be P times 6 feet cubed over 3EI. And then we need then this 2 feet, still going downwards here, so 2 feet times our rotation theta b, and that's where you come back again, you look here, and it's just serendipity that the rotation we want is also the max, and we got this equation already for us, PL squared over 2EI, And again, we have to use the 6 feet for that little portion of the cantilever that we're looking at. PL squared over 2EI. All right, let's get some numbers in here. The W is 5 kips per foot times the actual length in this case for that model is 8 feet to the 4th over 8EI, and then minus the P is 10 kips times our 6 feet quantity cubed over 3EI, and then minus, well, the 2 over the 2 is going to go away here, and we're going to have P times 6 feet. That's cubed. We get another, oops, sorry, that's squared. I was checking units here, and that's how I knew that there was a problem with the way I was writing that. That's over EI. Notice that we're going to have kip feet cubed in each one of these. Oops. 10 kips times feet squared times feet, that's going to be feet kip feet cubed. Kip per foot times feet to the 4th will be kip feet cubed. Alright, so now let's just get it all added up. 5 times 8 to the 4th over 8 is the same thing as 5 times 8 times 64. Plus, I'll worry about the minus sign in a moment, 10 times 6 divided by 3 times 36, plus, and then 10 times 36. And we get 3640. I think that's right. It's minus 3640 kip foot cubed over EI. Right, so that's our delta C 0. Now let's replace CY, our redundant reaction. Right? And so in that instance, we've got the unknown value of CY, and that's going to cause this to bend upwards. Okay, so now we've got this displacement to figure out, but we know what that is. That's PL cubed over 3EI. So CY times the length, that's 8 feet cubed over 3EI. That is equal to, let's see, 8 cubed is 512 feet cubed times CY over 3EI. 512 over 3 is not at all convenient, so I'm just going to leave it as a nice fraction there. Alright, now we've got to go and get then the final little piece. And so go to the next page here. We're going to write our compatibility equation. That's compatibility in our solutions to match with what has to happen in the real structure. Right? So delta C in the original structure has to be then composed of the delta CO that happened in the primary structure, primary loading, plus the delta C that happened when we replaced our redundant reaction. Right? Superposing what happens between this and this has to be back equal to our original. Right? And so we know that the final is 0. We had minus 3640 kip foot cubed over EI for delta CO plus 512 feet cubed times CY over EI. Right? And so now when we solve for CY, the EI's go away. That's kind of nice. We never really had to fuss with those too much. That's going to be equal to 3640 kip foot cubed over, I left off a 3, didn't I? A 512, and then there's a 3 there, and that's feet cubed, so that goes away. We'll be left with the right units, and we get 21.3 kips. The positive says we did this all in the correct direction, and from there, if you come back here, right, you'll see that's what we have here. How do you find the rest of these then? Well, you find them through, of course, equilibrium. That just comes from going back to our model of the original beam. There's your 10 kips, your 5 kips per foot. We now found out that was 21.3 kips, and AY, of course AX is going to be 0, sum of forces in the X, and we got our moment here at A, and now we just do your normal sum forces in the Y if you wanted to. I'd prefer not. I'd prefer, yeah, maybe I will. I say maybe I will because if I sum moments here, I got to have MA, which I don't have. I'm going to have to use the 21.3. So sum of forces in the Y is what's going to tell us that if we take 5 times our 8, that's 40 plus the 10, and then minus the 21.3, we'll get the 28.7 kips for the AY, and when we sum moments about, say, point A, we'll find out that the moment at A is going to be 49.4 kip foot. Right, so you'll just write your equilibrium equations to find those. Bam, we have the reactions. A lot of work, isn't it?